iniziando. So are we good to go?
Few more minutes for other people who are.
Yeah. Maybe. It's quite empty now, but let's wait.
You know. Let's just give them time to go for sure.
Hello.
Yes.
Gonna wait like 1 minute. Else is coming.
One more minute.
Yes.
And go.
Let's not be more Dutch than the Dutch, okay? We start on time, but not before time.
Oh, we have photos here. That's very helpful.
You were already.
I do get that impression sometimes, but no, definitely not.
Okay, it is 3 p.m. I will be chairing this meeting. Welcome everybody. This is the master's thesis presentation of Matteo, and I give you the floor. Go ahead.
Okay. So let's start from the title. The title of this thesis, we'll stay here. Title of
Would
this
you like
thesis
to come in and close the door?
Oh, yeah.
Thank you.
The title is Evolving SUPG-based closed-loop controllers for modular robots of arbitrary shapes. Let's break it down. There's a lot of work. I'm going to start from the modular robots of arbitrary shapes, because everything is being done in a framework called the Triangle of Life framework, which involves modular robots that can evolve the shape. So, this is the Triangle of Life. As I said, the idea is to coevolution, evolving both minds and bodies at the same time. And it's a triangle because its data is break down in 3 steps. First, you have the conception, in which you have like the blueprint of the robot, but you don't really have it. So you build it. Imagine 3D printing components, connecting, attaching the batteries, charging the batteries. And at the end, you have the delivery, in which you actually have the robot. But the robot is blank. It doesn't have a brain. The next step is to create a brain for the robot, so that it can do the most basic task and whatever task you want. But mostly you want it to walk around, so not having a static robot, so definitely that's very important. and but also to learn a bunch of tasks, depending on what you want these robots to do. And in this phase, the learning loop is started, and this learning loop keeps them iterating and learning more and more on how they, what the tasks they should do, and keep learning. Even after they become adult, this will not stop. They will keep learning and getting better. And then at the end, they become mature and fertile, so they go around doing their own task and search for other robots. And when they meet other robots, they're going to create an offspring, like, you know, animals kind of. And that new offspring is going to be a blueprint or a genome of a new robot, and the cycle starts again. So why are we doing this? Like, what is the purpose of all of this system? The idea is to be inspired by nature. So instead of building very specialized robots that do just one thing and they can easily break and require maintenance, is to create a system, like a swarm of robots that just continuously improves. One possible applications are like in deep oceans. There are like deep oceans are the only place on Earth left that we didn't explore, and just sending a microphone there is hard. So the idea would be to have some kind of evolving robots that would maybe crawl down lower and lower until we reach the bottom. Or another application would be nanorobots that stay in our blood and help our immune system. So because viruses evolve very fast, and this is a very fast evolving environment, you would need something that can adapt quickly. So you cannot have a static solution. You need a solution that evolves in time together with the thing that is fighting. And the last one is space exploration. What is the most unknown place of the universe? The rest of the universe, there is not Earth. And just sending robots, instead of studying everything and have this robot that works for 10 years without any maintenance, send a bunch of robots that keep iterating and evolving in shape and in mind with an environment without studying it too much at the beginning. But let's go back. This is like a lot. So the goal of this thesis, it was to improve over that learning iteration process. The state of the art that we have right now, it's just making the robot walk in any direction, but not walking to a goal. So we wanted to make it a bit smarter and really make the robot walk into a target. So we define a targeted locomotion for a robot that is modular. So we don't know the shape of it. It can be different modules combined in different shapes. But first, we want to check if the algorithm that we chose can actually move in any possible direction. So does it move? Yes. If it actually moves, then we can say it moves in a certain direction. So to make it simpler, we divide it into two steps. Reasonable gaits, so reasonable walking, and targeted locomotion. I want to give you an overview on how the robot looks like so you can visualize it better. So these are like robots in simulation, and these are the robots in hardware. We really built them and they work. And the modules are composed of the skull, which contains all of the brain, battery, and stuff. Then the joints, and these cubes that can act mostly as an exoskeleton and help to support the robot, but also as feet, and kind of build up the robot through these modules. So we chose all of these different robots as a sample. So we tested our algorithm on all over different robots. Over the line are the shape that increases in complexity. So spiders, geckos, snakes, and these are babies that we sampled from the parents above, because we wanted to test also a bit of asymmetrical shapes to keep it varied. Let's talk about the controller. Going through some literature and papers, we found this single unit pattern generator, SUPG, which is a controller that was quite good for the task that was applied to. They tried to make this robot, which was kind of a cat walking, and it did manage quite a good result. So we tried to implement it in our own. This controller works through a neural network, which is a pattern, a pattern-producing neural network. So it's slightly different, just produces better patterns than a normal one. at the center, and this is the evolved part, the configurable part. Then you have a timer, which is just an input, something like a sinusoidal input. So, but instead it's just a linear from 0 to 1. And the really interesting thing about this controller, different from others, is that it has a trigger input. So the trigger can reset and goes to 0 before it finishes the cycle. And the idea was that you had this cat that could walk over not a stable terrain, like a bit with rocks and stuff, and instead of going through all the cycle of walking, it would touch the ground, reset the trigger, and start to lift it already. So that is why it was quite stable. And the last interesting part is this X and Y inputs. You have only one controller, one network for all of the robot. So every joint shares the same network. What changes are the inputs. So the same network, if it gets 0, 0, is configured to run for one joint. If it will 1, 1 is another joint, and the inputs are the coordinates of the joint. But a bit more about the substrate and its coordinates later. This was not good enough. We needed to modify it a bit. And this is the modification that we made. It's mostly about this trigger because our robots are not like so nature inspired. Like just defining a feet is a bit hard. And also inputs like touching is not a simple task. So instead we wanted the network to figure out on its own when to reset itself. It would have sensors, so it knows a bit around, and from the sensor it would need to understand when to trigger the input, and if the trigger was above 0.9, it would reset. Yeah, the other modification is we added the sensors because we needed the robot to know where the target was, and we made everything online in the sense that everything is running on the robot on its own, so there's no mastermind that is controlling the robot. The robot can run without any network connection, just on the Raspberry Pi computer inside. This was the controller. Let's talk about the learner. The learner is the thing that configures the controller, and as I told before, the configurable part is the network. The network is a neural network evolved by NEAT. And NEAT is short for Near Evolution of Augmented Topologies. It's very simple, to be honest. It's starting from a really scratch network. So imagine inputs and outputs. So outputs in this case, this is an example with Super Mario. And outputs are just the buttons to press, and inputs are the map reading. And completely empty, and it will start slowly to add complexity. Add a connection there, split a connection with a node. So it starts simple and grow complex, and the result, the ideal result would have the minimal connection possible. It has historical markings, which just means that it marks every node when it's created with a unique number. And if you want to offspring, two offspring have if you have two parents and want to mate with each other, you need to know if they are compatible. And if they have enough nodes that have the same marking, it means they are compatible. And another important thing is that they are these species in this algorithm. So you always compatible controllers are inside the same species, and species are kept small and varies in number. So you would have not a local maximum trap, but you would expand through different solutions. So. Then we have HyperNEAT. HyperNEAT is inspired from NEAT. It's using NEAT to create a network, a CPPN network. And the network is used to configure another network. Now, I don't want to talk about this too much because how we're going to use it is a bit different. We're going to remove this network, and in here, we're going to place the joints. So every joint of the robot, or just imagine the robot, the spider, placed here, and every point is a joint. So every joint will have a coordinate. The coordinates are passing in the CPPN, and then the output is the angle of the joint, and that's continuously run. That's how we configure it. And this idea of using coordinates is borrowed by the HyperNEAT, and that's why we mentioned it. Why HyperNEAT? Like, why all this complication? The most important things about HyperNEAT is the ability to exploit symmetry. So if a robot learns how to move the right leg, it can just recycle whatever it learned for the left leg. These are examples on outputs of HyperNEAT, and as you can see clearly, there is definitely symmetry, and this is also not axial symmetry, also central symmetry. So we can definitely re-exploit. And the other interesting thing is that you have to learn one network in with this method. Instead of having one network for each single joint, you would just have one network to learn for all of them. That simplifies the problem a lot. So let's talk about how we fit learner and controller inside our environment. We have, I'm going to start with, are we doing it in hardware and software? And the answer, sadly, is only software. We only did simulations. We wanted to do a bit of hardware as well, and in the back of the mind, there's always the idea of putting back into hardware, but we never managed in the end. The software to run it is Gazebo, which is a pretty famous robot simulation environment, and Revolve is our own library wrapper to use it. The software that was written for this thesis, it's easily simplified with this scheme. Everything needs to be to run inside the robot. So learner, controller, evaluation, everything is inside the robot. The learner is a unit inside that generates new configurations of the controller, one at a time, and then a new configuration is added. The controller is used. At the end of 30 seconds is evaluated, still internally with sensors inside. That evaluation gives a fitness, which is given back to the learner. After a while, the learner collects enough data on how good were the controller and recombines the good one to get improvement over and over. Now, this is like generally, and how did we do the Phototaxis part? So remember, we want this robot to walk to a specific direction. We want a target, and the robot should walk to the target. How we did it was place the robot, place some targets, make the robot move around, and at the end see how good it was to that target. And then move the target to another place and test again, move to another place. So first test how good it was to go to the center, then to the left, then to the right, then very left and very right. And all of them, those tests were combined in just one fitness that was fed in to the learner. So a good controller ideally is able to go to all of the different targets and possibly new ones. This is it. Let's talk about the results. If you remember, we started this saying that we divided the controller in two parts. The testing of the controller in two parts. First, it was gait learning. So just, does the robot walk? Any direction, we don't care, it just walks. So the answer is yes. The results weren't so great, but we did get results, so we tried to improve it a bit. Because the robot starts completely blank without any connection, we started hard coding in one connection, and there's like this kickstart that we did. And it did improve. So these are the results normally, like vanilla with the normal one. And we reach 1 centimeter per second in the end, at least for all the different robots. And this is the improved version. So like not only here, but also statistical test, it does improve for real. The lines are the different type of robots, so there's not too much difference in between them. And the columns are different configurations, but I don't want to focus too much because I tried different configurations of NEAT and none of them were different. So I just chose one, which was phase 10. And 10 is the population size and phased is the type. And these are the statistical tests. Like none of them are really different from each other. Just choose randomly. Now about the phototaxis part, or the targeted locomotion part, we didn't achieve the results that we wanted. We really wanted the robots to follow the light, just move the light around and follow it, but we didn't achieve it. We tried the kickstart approaches before. We did get a bit of improvement, but not good enough. And then if you remember, we had 5 different targets. all at the same time. So instead, we separated all of the targets into single targets. And just try to learn to go to the center one. And then just try to learn to the left one. And try to see what's the difference is. And we did find something interesting. So first, this is the vanilla one. And this is the kick-started one. And the fitness is how good it is to reach his own target. Like as a sum, all the targets. Oh, sorry. And only, I will tell you what to read in these charts, only the blue lines are the one that really improved. Like this one. The blue lines correspond to the simple robots. So only the simple robots who went with less joints were the one to actually improve. And I believe this is a sign that our problem is too complex. So when the problem is simple enough, then it gets a jump in improvement. When the problem is not, and it's too complex, even a bit of improvement doesn't really show any sign. So it needs to be simplified even more. And then, again, I told that I separated the different targets and have them learn separately, just go to the center. I compared that to learning all of them together. And we did get an improvement, a significant, so this is the p-value to compare, so all of them are significantly different as results. And the improvement is sometimes very significantly different. This basically tells us that simplifying the problem gets much better results. Again, like the problem is probably a bit too complex. I have a small video to show you because only numbers is a bit abstract, so I wanted to show you the robot themselves. I took one robot and with one controller, the best I could find, and placed 3 different targets. One here, and one here. They're barely visible, but they are there. And right now they start exactly the same, but after some time they will start to move into different directions. So in this 30 seconds pass, so the evaluation is finished, and they are not evaluated anymore, but we keep them running because we want to know what happens. If we go a bit forward, things start to get a bit more interesting. So this robot wanted to go here, and quite good. I'm quite impressed by the result. This is where things get a bit tricky, because one of the 2 robots wanted to go here, and one of the other 2 wanted to go on the opposite, and they're both going to the same direction, which is a bit weird. And if we keep going forward, the central robots start to move randomly, but probably all of them start to move randomly around. Here we are at 3 minutes past. And yeah, the situation doesn't improve too much. This robot that achieved the point, it was the one supposed to go here. So don't say hooray to anything.
Matteo.
Yes.
Did you always get the same results? Did you redo this test?
Yes, like this is one of the best. I tried also to replay others, and they were even more erratic than this one. So yeah. But I also tried to see the results of some data of a single experiment, and there's some trickiness inside. So did we achieve our goal? Yes and no. If you remember, our goal was first to get reasonable gaits, to have the robot moving, and we did get around 1-2 centimeters per second, which is good enough for those little robots. Yes. But did we achieve targeted locomotion? And the answer, I'm pretty sure we can all agree, is no. It's not very great. But we did achieve something interesting. We did achieve directed locomotion. The difference here is that targeted locomotion, you have a target, and if you move the target, the robot is supposed to follow the target around. Directed locomotion is very different. It's teaching the robot to go straight, left, right, or maybe teach him to rotate. And we did achieve it in the separating the targets. So if we teach the robots to go only forward, so I have the target only forward, that was much better. But that was a different task. That was directive, like just go forward. Don't care where the target is. So again, the same theme applies. The problem was a bit too complex. If we try to simplify and have a simple problem to solve, then the improvement is much better. So, at the conclusions, we try to take this neat algorithm or this SUPG controller and just black box. Just give it a task, please go to the target. That's not a good enough approach. We need something a bit more thought of. Like, we need to know more or less what's happening inside. And the algorithm is a bit too simple. Neat has a limit on complexity that it can grow. At some point, it's going to start to kill the too complex networks. It's going to give priority to the simple ones. And we didn't have enough time. So it is possible this method would work, but it would need more of a deep learning approach. So this was already 23 months of simulated time. Like in hardware, because the simulation can be accelerated, but it was still a lot. But maybe having much more time, it would have gone somewhere. But we didn't take this approach because we wanted to have something feasible for robots. Just to give you an idea, these robots that we have, every half an hour they require maintenance because some parts breaks. So 23 months is a lot of maintenance if you want the robot to learn. Well, things are not finished. We learn something, we can improve. Sadly, I don't have the time to do it. I hope someone else will pick it up. First and most important idea is to modularize the design. So instead of having a controller that does everything, have more controller, every single one does a simple job. The best idea would be to have a controller that knows how to move forward, have a controller that knows how to rotate left, and one good rotate right. And then, depending on where the target is, alternate between these controllers, move around, go forward, rotate, go forward. And you can even improve a bit. You can also add strafing, and maybe some robots are better at rotating in a way, or some other robots are better at going backwards instead of rotating 180. But anyway, the idea is to learn simple tasks and then combine them later. So less of a black box approach. And about learning time, we could also think about improving and have more learning time by mixing hardware and software, having simulation and reality collaborating with each other. You have one robot walking in real hardware, just crawling around, and then at the same time, the same robot other 10 times in 10 different simulations. And all of them combining the data on one robot. So we still have one robot that keeps attached to reality, doesn't start to exploit physics jump or something in simulations. But you still have 10 times more the simulated learn time, and that would improve much more the knowledge that you have. That's pretty much it. I have nothing else to say. Thank you very much.
Thank you.
So time for questions, and I have a lot, but I want to give others go first. There you are. Okay, so could you go back to that slide where you have a table showing all the 5 directions? No, a table. With the results included.
Here.
Yeah. So what is really very surprising is the huge difference between left and right, and even more difference between more left and more right. This is something which is really surprising, because you would say it is, it's neutral towards the direction. I could understand that it is not neutral towards how far are you from the middle line, but whether you are left or right from the middle line, why is that so important?
It's a very good question.
Can I ask
it's his master's student.
No, but connect the question to that.
Oh, okay. You don't want to give an answer.
No.
The question, good.
When you were testing different targets, what was the order of testing? Just like you declare there, left, center, left, more
no.
left.
Center, left. center, left, right, more left, more right.
Okay.
To give you a translation, more left were the one like very, very left. Okay.
But this is the results, this is the table of the results of the separated.
No,
So
no, these are not the results. This is the comparison. So what really tells is that
Yes.
if I try to learn everything
Yeah.
and I go left, or if I try to learn going only left, then if I try to go only left, I learn much better.
Still, my question is the same actually.
Why,
so
yeah.
why is more left so much different from more right?
Well,
Is there anything in the shape? Which shape is this?
not all of the shapes were symmetrical. We had some babies, and what this really tells us, like left improved a lot, but right, it did improve. Like there is a significant p-value, so the values are different, but only 6% better. And I'm not really sure. No.
Okay.
The only thing I can say, maybe this because some shapes were asymmetrical and influenced much more the results.
Have you ever made a table split by the shapes? Same data per shape. Because this is for all shapes together, right?
Yes, exactly. You mean between separated targets and unified targets?
Yes.
Yes.
But then per shape. So maybe the one another shape.
Yeah, this is one shape before, like joined and separated, and this is spider 13. These are all the spiders.
So how does it look like for another shape? Spider is
And then to read it, the same color means the same target.
So spider is, can you show us a picture of a non-symmetrical, asymmetrical shape?
These are the asymmetrical ones.
So here the differences are smaller.
More left. More left. This is way different.
I don't see any relationship. So it remains a mystery.
It remains a mystery.
Okay. The other question is the choice of the mechanisms. So you wanted to test one particular mechanism. That was your assignment, your self-chosen assignment, which you succeeded in because you tested it very thoroughly. Okay. And I understand that the disappointment that it doesn't work, but your work is still good. I mean, you did what you wanted to do.
Yeah.
And when you thought about what next, you said modularization.
Yeah.
How would that go? So, could you name a few modules that would be helpful to have?
In my ideas, is to have the main thing is to have very simple modules, because you want to learn the task as simple as possible. Because if a task is simple, then it's learned very fast and it's feasible to learn it in real hardware or with small net amount of simulation. So as a target for a simple thing to learn, it's probably directed locomotion. I would go for that. So have a controller just learns how to move forward. That's the only thing it needs to do. And then you have a module that asks the robot to rotate. And then you would like write something on top of it that knows using this controller would rotate, this controller would go forward, and we just read the sensor, establish more or less where your target is, and use these controllers to move around. So the supervisor part that just manages all the module, that's not machine learning. It's just hard coding the code, like writing the code your own, if this then that. What could be modularized as well? So in this example, we had only 2 sensors, which will always in the skull, always in the same position. But in case of modular sensors, so different sensors and different robots, then you could write also a module on how to where is the target depending on all the sensor readings, and then you need to evolve this module that has an input as all of the sensor, as an output as where to go for the target.
And the next one is a very naive question, maybe even childish, but I was sailing in the summer.
Okay.
And you cannot steal a boat if it is too slow. So could this be something to do with your thing? That if the robots were quicker, it would be easier to steer them into a certain direction?
Ah, okay, I understand now the question.
Maybe they're just too slow and this is why they are going everywhere? If they were quicker? I don't know, but you have more intuition because you were more with
Yeah.
them.
Well, kind of. I think they learned it to. They needed to learn how to move and where to move at the same time. So in that sense, quicker would be you already know how to move. So this is a completely other approach, not modular, but you would have this controller that already know how to move, and then you would start from there to learn to go into a certain direction. And maybe instead of using this approach to learn how to move, you could use another controller, completely different, and then transpose that movement pattern into this brain, and from there start to modify and have the understanding of the surroundings. That response? Because
it remains a speculation, but indeed, yes.
Because no, I don't
okay.
like. The point is that it takes a bit of time first to learn them how to move,
Yeah.
and after they know how to move, they need to learn to distinguish the different directions.
Okay.
So that's why they're not so fast.
Can I ask a question?
Yeah, go ahead, sure.
Did you notice some difference in performance, let's say, like the robots who were performing better in general? Are they more symmetrical or less symmetrical?
So no, the only thing that I really noticed is how simple robots can learn much better.
Mm-hmm.
But
Simple meaning small? What does simple mean? Small?
simple means a few number of joints, so small. So that simple means less parameter to learn, like less complex things to understand about your own body, and they learn a bit better. But apart from that, I didn't notice a significant difference, like a significant jump between one and another.
Okay, sorry. Back to the question. They're all symmetrical, as I recall, but the
Not all of them.
E-shaped robot. No, but yeah, there is the.
There are some of them which are not. Here it is.
Okay, so the last row.
There is baby A, which is a mix between gecko and spider, and baby B, which is, I think, a mix between the snake and the gecko 12.
How about the snake robots? Do they learn to hear at all, or?
Oh yeah, wait. The snake had something interesting about them. Separated. Where is it? Gecko, snake. So. No. Okay, the snake has some difficulty because of its shape to move around. What I remember is the gecko. The geckos have significant good gaits to moving left and right. I believe they're just strafing, like a crab. So that's something that I noticed.
But can you then compare that? Are there snakes and geckos with the same number of joints? Because then, if there's then a difference, then you could say, okay, it depends on the shape of the robot.
They don't have the same. Some of them have the same amount of same number, but it's most. They don't have this. Like the middle one, snake 7. 7 stands for the number of joints,
Yeah.
and the gecko starts at 7, 12, 17. No, they don't correspond into complexity.
You do have, but you do have 7 as a.
I do have, but I
joints,
didn't think about doing a comparison between gecko 7 and the snake 7.
Any other questions, or you want? Please go ahead.
You said you had like 23 months of your time, but
Yeah.
not for one robot. But
No, no, this is it's accumulated all of the data that you see, but I did test at least twice that, like stuff that I didn't show, like preliminary test or some extended test, because I wanted to see, okay, 2,000 evaluation, but what happens if I give 20,000? This actually learn something. I did get a bit more of improvement, it's nothing extraordinary.
And were the simulations faster than real time or slower?
They were faster, so 23 months were done in, I think, 1 month, 25, like everything goes in 25 days of simulation. But I used 12 cores, the 12 simulation in parallel at the same time. Otherwise, single CPU would be 9 months. Yeah.
Yes. Okay.
Thankful for multi-cores.
Anybody? Gongxin? Any remark, question?
Okay, so you mentioned you use the SUPG as a cover, right?
Yes.
So we have those like CPG, SUPG. Why you use the
Okay, I did choose this one because I started with the question, can I move it to a target? And from that question I went into literature, tried to search for papers and research that's been done, and it's amazingly little the amount of stuff that is out there for targeted locomotion for legged robots. Because if you have wheels, it's pretty simple. Just rotates the wheel faster in the direction you want to turn, and that's easy. But if you have legs, you really have to learn how to move first, and then to variate, to turn, and everything. So I just choose this one because it seemed promising, and they had a walking robot unstable. But at the end, maybe it wasn't a good choice, because in the paper there were a lot of assumptions about their specific task.
Questions from guys.
Okay.
So they want to know, how did you choose the shapes?
Where are the shapes? So because guys, I'm streaming it on YouTube and there's some other people watching it.
Yeah.
These are the shapes. So we started with some basic shapes. These are our starting ones that we chose at the beginning. Spider, gecko, and snake. These are our basic ones. They were inspired by nature. We needed to start somewhere. We cannot say start completely empty. And then we chose to have bigger version to see what's the influence, like how big can we grow them and how much of the improvement we have. And we had babies because we wanted also to test how good it was in mixed version of these robots. And these robots were chosen also for other research and publications, so we just kept the same shapes, which is more comparable to other papers.
Is it general to use, I'm not a robot expert, but is it general to use squares instead of round figures? Because you're making the relationship to nature. I would say round is a figure you see much more in nature than squares.
It all comes
Maybe that's
down.
a completely different subject.
It all comes down how difficult it is to build, to have a modular design for robots. We chose this because it's quite easy to swap in, so there's no, we just insert them, and these models are 3D printed. Well, with the sphere one, it would be a bit more difficult to compose all of the modules. But this was outside of my thesis, as part of a bigger project.
So the answer to that historically is that when we started this project, we wanted to limit our efforts, and whatever we could find out there in the literature, we were happy to adopt. So the whole design, the choices for this kind of components is from someone else, another researcher who was in Switzerland back then. So we involved him in the first project. adopted his design.
Yeah.
Okay, if there is no other question or remark, then I thank you again. Well done. So what happens now? The two of us will sit down
Discuss.
for 5-10 minutes and then evaluate you or give you a grade. And you can wait here or in Milan's room or where can we find you in 10 minutes from now?
I was thinking maybe a bar or somewhere. Because of all these people, I don't want them to fit in. And
Well,
Yes,
we can just come here in 5 minutes.
I can come back whenever
Yeah.
you say and just
Okay, so be back at 4, okay?
meet back at 4. Okay,
Yes.
good.
Yes. Right.